Once we've established our critical points that we have to check for, we're going to test our slope. So we're going to test the slope. In this case, we want to test the slope some point left of that coordinate. So if I plug -2 into my derivative, I'm going to end up with like 0.02, I think it is. Okay, so it's going to be positive. So we know that it's got a positive slope through here. And then going across that, we're going to test our slope at 0. So our slope at 0, when we plug it into here, we're going to end up with, it looks like a negative number here minus a positive number here. So negative minus a positive is going to give us negative. So we're going to have negative slope in here. So it's going to come down like this through there. Okay, so maybe I'll just draw this a little bit better so I can see it. It's going to kind of come down like this. So what's happening there? Well, we're going to have to check that. Okay, and then test the slope at +2. We're going to end up with, it looks like if I plug that in, I plug +2 into this expression, I end up with the same positive slope as I had for -2. So I'm going to end up with positive like that, and it's going to be like that. So there's no zero slope here, but it goes up. There's no calculable slope, and it comes back down. So what's happening at that point? Well, we kind of have to analyze this and know that it's going to go up and then change abruptly like that. So this is something called a cusp. Same here. It's going to come down and then change abruptly like that. So this is still a vertex, although we cannot establish the derivative at that point, okay, because derivatives need smooth and continuous. There is a point there. It's not an asymptote, so it's going to go up and then change abruptly, and we're going to get a kink in the graph. So that's how we need to think of analyzing this. We haven't finished the second derivative, so we'll do that first before we draw the full graph. Okay, so this is something called a cusp when we get this shape like that. We're going to end up with this. These points are called cusps. Okay, so let's take a look at generating our slope chart for the second derivative, our concavity chart. So we need a second derivative. So my second derivative, starting with my first derivative, I'm going to use the original expression up here. So this one here, to generate my second derivative. I'm going to use my power rule, so -2/9 x minus 1 to the power -4/3 minus, so it's going to be plus 2/9 x plus 1 to the -4/3. Okay, so that's my derivative. I want to solve this and make this equal to 0. Okay, so when we simplify this expression, we can make them equal to each other again. So we're going to end up with x minus 1 to the -4/3 is equal to x plus 1 to the -4/3, since one is positive, one is negative. So when I put it to the other side, they'll be equal to each other. And again, we can't necessarily solve this algebraically very easily, but we can look at the powers here. These, again, have even powers. Although it's in the denominator, they are even powers. In fact, we can, cross multiply this and actually make them positive powers. It doesn't really matter. In either case, these are even powers, which means that this resulting value must be positive, and this resulting value must be positive as well. And again, by inspection, we can solve this equation by saying, well, at x equals 0, I'm going to end up with +1 equals +1, so that must be a solution. So x equals 0 is where my second derivative is equal to 0. So I'm going to put the 0 in here in my concavity chart. I'm going to get that equal to 0. So there must be a change of concavity there. We also have, well, there is a potential change in concavity. We have to check the non-differentiable points, because we know that these are not defined at x at plus minus 1. There's restrictions here. So we have 1, 2, 3, 4 regions that we have to check concavity for. So when I test my concavity, I'm going to test x equals negative 2 into this expression. So when I test x equals negative 2 into that expression, we're going to have to analyze this value. Now I can just plug it in and see if it's positive or negative. Okay? But we could also do sign analysis. This is an expression in the denominator. Okay, so this negative means it's in the denominator. If I put negative 2 into here, that means that this denominator is bigger. Okay, so negative 2. This denominator is bigger, which means that, this denominator is bigger compared to this one. So it's going to be negative 3, negative 1. So this denominator is going to be bigger than this one, meaning that this negative number is going to be smaller. That means that I end up with a negative, smaller negative, with plus a bigger positive, small, big, that's going to equal positive. So this is going to be positive. So my concavity out here, I'm going to have a positive concavity. So it's curving up. So what's happening is it's going to curve up to that little cusp point that we have. I need to then test the second derivative between negative 1 and 0. Okay, so between negative 1 and 0, we'll maybe test negative 0.5. Okay, so when I plug in negative 0.5, I'm going to have negative 1.5 and positive 0.5 here. These parts are still going to be positive, so we're going to compare this negative number here with this positive number here. This is negative 1.5, so this is going to be bigger compared to 0.5 here. That means that this is going to be a bigger number. Okay, so it's going to be a bigger number here and a bigger number here. So what does that mean? It means that it's going to be, I'm going to end up with a positive concavity here. So we can do this sign analysis. Now it may be easier just to plug in the numbers and test the concavity that way. So I'm just going to plug this into my calculator to make sure. So I've got negative 0.5 minus 1 to the power negative 4 over 3. When you plug this in, you've got to be pretty careful with all the brackets. Plus 2 divided by 9, bracket, negative 0.5 plus 1 to the power negative 4 over 3. Okay, I'm just making sure that I have the right brackets in here. Okay, so I end up with positive 1.178. So it is in fact positive. Okay, and then again I do the same thing here. I'm going to do 0.5. This one I'm just going to plug into my calculator. And I end up with positive on this side. Okay, oops. It's going to be positive 0.5. Okay. So I'm going to end up with negative, I think, on this side. So this is positive, positive. Okay, this is going to be negative here, curving down, and looks like this is negative as well. Okay, so y double prime at 2 is going to be equal to, looks like it's going to be negative. Okay, so I end up with negative here. Okay, so those are my concavities. It's going to look like this. So what does this look like when I put it all together? Well, before I put it together, I want to have, I've got my concavity chart and my slope chart. I'm going to make a table of values of the values that I know. So y equals, we had a 0 at 0, 0. I had that point at negative 1, positive 1. So I'm just going to plug negative 1 and positive 1 into that equation. And if I put negative 1 into here, I'm going to get negative 2 squared cube root, so cube root of 4. Okay, and then if I put positive 1 into here, I get 0. I get 2 square cube root, so it's going to be negative cube root of 4. So this was positive cube root 4, negative cube root 4. So I'm going to plug those points in. Negative 1, positive 1, and looks like those are my points that I have to be careful with. It's going to be negative and positive right here, so that's going to be cube root of 4, and I'll make this point about here, symmetrical, negative cube root of 4. Okay, so those are my points. Following my slope charts, it's going to have an asymptote along the x-axis up to here. It's going to be curving down like this. It's going to change concavity across there like that, and then it's going to curve like that. So there's what my graph's going to look like. It's going to have this kind of, I should just draw this in a little bit nicer than that. Curve down like this and curve along the asymptote like that. Okay, so this is what my graph's going to look like. And lastly, what I'm going to do is a candidate test. And a candidate's test is just testing for min and max points. And the points that we have to test are any vertices where slope is equal to 0, any undefined slope points, so these 2 points here, and any end point. So in this case here, when I test this chart would be the same as my candidate's test. And I can see that from my chart, I've included all the potential points of mins and maxes. This represents then my min point. This represents my max point here.